Okay, we may proceed. The next two sessions are about 3D on the web, so the web UI chapter of FIWARE. My name is not Felix, I'm Stefan. I'm just jumping in for a colleague. To speed up, as we are now all warm, we will treat about 10 enablers in the next 2 hours. We will start with the 3D UI generic enabler called XML3D, which is the core enabler of the web UI chapter of FIWARE. We will provide a quick motivation, several examples and applications, and a quick crash course on this one, followed by several other GEs that are relevant to the domain of web UI. The general idea, so let's start with this. This one. The web has evolved from an information medium to an ubiquitous application platform. You can find in your web browser complex social media pages, map applications, video broadcasting services, or a whole office suite. All this is possible thanks to the continuous evolution of the web. So it started with text and images, and today we have support for complex 2D graphics, video and audio, and of course we should not forget about 3D. The modern web supports 3D today, using WebGL, which provides a powerful hardware-accelerated 3D without any plugins. But WebGL has its problems as well. First of all, raw WebGL is very complicated for the usual web developer. This becomes apparent when comparing WebGL with regular HTML. The beamer's rather bad. So HTML is declarative. So we describe the content. It's high level and overall pretty straightforward. WebGL, in contrast, is imperative. So we describe process, how to create content, which primitives we draw, and so on. It's low level and, as a result, pretty complicated. We want to have 3D graphics to be more accessible. So there are several libraries that help with this regard. For instance, 3GS might be aware for a few of us. However, there is a second problem. So WebGL is imperative and is almost entirely disconnected from the DOM. Only connection is through one canvas element for the whole 3D scene. So this isolates WebGL from many other web technologies when using events, CSS, and popular libraries such as jQuery or jQuery UI. The goal is to find a declarative format for 3D graphics connected to the DOM. The ultimate goal is to make 3D accessible to non-graphics experts, so the usual web developer. The current approach is the creation of a polyfill implementation. This is just a JavaScript library that can be hooked into any web page, and it will implement the declarative 3D standard based on JavaScript and WebGL. Thereby, no specialized browser or no plugins are required. Today, it runs out of the box in many modern web browsers. Our proposal for declarative 3D consists of two technologies. The first technology is XML3D. and the beamer is really bad. So there is a cube rotating on the left side. A black cube with a logo on a dark background, so it might not be the best choice. So XML3D is a minimal extension to HTML5 for 3D graphics. It tries to keep the set of new elements minimal, try to reuse as much from the web as possible. For example, CSS transformations. XML3D also features a generic core, declare type data, for instance, float or float3, so vector types. Mirrors the buffer to modern GPUs, and there's no conversion overhead required. So as you can see, there is a usual HTML document, and the XML3D is a newly introduced DOM tag, and has some domain-specific like groups and meshes to represent the content of the 3D scene. The second technology is Xflow. Xflow is designed to handle complex data processing that usually comes with 3D graphics, for instance, when doing character animations. It allows the declaration of data flows inside the document, and these data flows are automatically optimized and parallelized by mapping the processing on the vertex shader. Xflow features a generic design with small and reusable operators, and it is possible to create custom Xflow operators. There is some wave animation on the left, and on the right the respective code. So there is the compute attribute of this data block that in fact represents the geometry of this mesh, and there is the xflow.mywave operator that modifies the generated grid that is generated in the embedded data container. Let's see a couple of examples. This Rubik's Cube application shows the combination of HTML and XML3D content for one application. We attached regular DOM events, like I have to do it here, like the on-click event and the on-mouse over to highlight, and the on-click to insert new geometry on this Rubik's Cube to implement the interaction. Additionally, we have HTML5 buttons that modify the 3D scenes, a shuffle or a reset button. They are somehow scrolled out because I had to reduce the resolution for the recording. Well, so the 3D scene is actually embedded into the HTML DOM. Here we have some character animations based on Xflow. This simply demonstrates that XML3D and Xflow support interactive animated 3D graphics. By the way, this animation runs twice, so in this browser window and in this browser window. As you might already notice, the slides are made using RealJS, so it's an embedded live demo into this HTML5 slide set. But Xflow is not limited to 3D graphics. We can also do image processing. This demo here is in effect disconnected from XML3D and simply applies processing on rectangular images. However, we can also combine image processing with 3D graphics. Here we have when it starts loading. Yeah, the Wi-Fi connection is as bad as the Beamer colors are. Well, just try again. So we do augmented reality using a fiducial marker and there is a teapot jumping on this marker. So the teapot is rendered using XML 3D. The position of the marker is determined using an image operator in Xflow. Well, now it's run there as well. So there is another demo of this when two markers are visible and the teapot jumps between them, and yeah, can imagine much more. In this section, we will present several real-world applications based on XML 3D and Xflow. So this is used in industry to realize some products. For instance, this is an old application created for the RTT Excite exhibition. It's 4 years ago, where the user can customize the car by dragging parts on the right over the car on the left. The part icons were rendered in 3D as well, and this demo still used the custom browser to render 3D graphics, but then with ray tracing instead of rasterization. WebGL just came out around that time as we made this demo. No. One back. This one. This demo was created in cooperation with Share Management, so it allows the layout planning of an Adidas shop. Users could place furniture and products, so the product placement was automatically adapted on sales data, and so to have an iterative process to optimize the placing of products. It also featured scanned 3D models of some of these products. The third one is training for disaster management. So that's an editor to, and this is a video that should run, or even not. Yeah, it might start. However, this is to place the vehicles in some disaster scenario to train people then in virtual reality environment, and where the training itself is done. So this editor is for the planning of those scenarios within the browser, so you have a collaborative environment to do so. This video works. So there is another collaborative application where we plan the construction site. So there is a lot of logistics going on when doing some construction. This is used to plan where to place the vehicles and materials and so on. And depending on the construction phase, there is also some verification done that the distances between two things are met and so on. Another collaborative application to review CAD models was done together with BMW. So parts are usually designed by many different parties, so there is a lot of communication overhead, and this can be simplified by a synchronized web application. So everyone can annotate parts of this model and thereby trigger discussion. This review using the visualization was finally done on a large power wall at BMW. This application was done with the University College of London and AERP, which is a mineral company. And this features a simplified visualization of the King's Cross station. This 3D model was originally related to ease the communication for the renovation of the station, because there were over 100 companies participated. However, these efforts failed in the past because the 3D model was visualized with the game engine, and it's difficult to provide custom applications to all those companies. Today we can visualize all this directly on the web by just sending a link to the company and immediately see the results. Also interesting is the visualization for the public. There's another EU project that already ended, which is the WebTundra project. This focused on an e-health application for Parkinson's disease. So patients suffer from the so-called freeze of gait, where the movement block for a couple of milliseconds to seconds when they pass by doors or small aisles. Because of these conditions, patients are afraid to go outside, and this virtual training was to learn to cope with the freeze of gait. So to confront people with freezes in virtual environments, this was using a Wii balance board and the remote to navigate through some kind of maze that was edited by some medical doctors to do studies on that. Finally, there is the fortress city Saarlouis. So our research department is placed in Saarbrücken. So Saarlouis is a city nearby, and as we are near the French border, there was a lot of conflicts between Prussia and the French in the Saarland region, and there was a fortress at the city of Saarlouis, and we made an interactive 3D city model, which is a virtual reconstruction of this fortress city, and that's exhibited in the City Museum of Saarlouis. Okay, now we will go into more detail how this will work, and start with a crash course for XMR 3D and So well, that's okay. To enable XML3D, all that is required is linking one JavaScript library to the HTML document. So this library needs to be included first, even before jQuery, due to some overrides in JavaScript. And the library essentially implements the XML3D and Xflow standard based on JavaScript and WebGL. So the example code is given there. The library is available over the website xml3d.org for download, but also with the FIWARE releases of the GEs. And all that is left for declaring the actual 3D scene graph. So to place a 3D scene within your web page, you need to create an XML3D element first. This element can be placed anywhere in the web page, similar as you would include an image. By default, it behaves like that, or a canvas element. But it can be styled any other way using CSS. It is possible to place any number of XML3D elements in the same document, but nesting XML3D elements is not supported so far. So as we can see here in this example, there are two scenes, both encapsulated with an XML3D element in the somehow light white HTML document. A basic transformation hierarchy is created with group elements. So each group may define transformation and transforming its content. So we use the already available CSS3 transform property to define these transformations. As you can see here, each group has a style attribute, and this style attribute defines the transform property, and the which transforms are possible are given at the Mozilla developer network with much more details.
Can you use the class attribute as well?
Not yet. This is an upcoming feature because well, you can, but you can't change it dynamically because watching these events is somehow tricky. Indeed, it's feasible. We use this every day, at least for the outer XML3D element, to style this and embed into the web page properly.
But you can actually use the class attribute, but you cannot expect if you modify the...
if you change the class of a group... Right. But that's an issue of the browser implementations with the CSS properties. Okay, by the way, don't hesitate to interrupt me if there are any questions. The angle from which we view the 3D scene is defined by the view element. So a view element can define its position, its field of view, and some other properties. The position and direction of the view are then transformed by the hierarchy, and the default view direction is the negative z-axis, as usual for any 3D graphics application. A scene may contain multiple view elements. One of these views can be selected using the active view element of the XML 3D element. The element needs to be referred by document ID. So there are two view elements in this example scene, and the first one, V1, is referenced by the XML 3D element that contains the scene. This can be changed dynamically to switch the view of the scene, for instance, when pressing a button or changing some radio box. Finally, we add actual content to our 3D scene. To add a 3D model to the scene, we use the model element. The 3D model usually refers to an external file that defines geometry and shaders. We currently only support specific 3D formats, but we provide converters, for instance, from Collada to XML 3D file format. To correctly illuminate the scene, we also need to define some light source. We do this with the light shader and the light element, while the light shader defines the type of the light and its configuration. The light element places the light itself within the transform hierarchy. Note that the light element always needs to refer the light shader element to get its configuration. Okay, in this example, we have all the elements present so far. The following can be done, for instance, in this scene. We have the light shader element here, which has its configuration like the intensity and the direction, and we can, for instance, change the color of this light source to red. So now the teapot appears like red shaded. Moreover, we can, as the beamer is pretty dark, increase the intensity at all. Thereby you can see also that we illuminate the whole scene, so the box and the Team Fortress guy, I don't know which one is it. Moreover, we can change transformations. So well, note that this transformation is done in the style attribute of the group that can be changed, like moving the cube a little bit more over there or up. This one. So what I do manually here, you can also do dynamically using then JavaScript to change content of the scene. We have 3 models here, which are referenced using external files. So there is this assets XML, and then the fragment is used to reference the respective asset inside of this XML file. And we can, for instance, replace the sniper with the Medic, I guess. Or it's For some reason it does not update this one. Assets. Or I forgot to include the other models. However, by changing, we can add another teapot at least. Yeah, obviously I forgot to include the other Team Fortress guys into this asset document. But by changing the fragment of the URL that references the model, we can easily change the asset. We can also change the viewpoint that is over there, like we can move a little bit more away. So you can dynamically edit your scene using a simple text editor, like you would edit your web page. Okay, as with any DOM element, you can attach events. In XML3D, we support all common mouse events. So the event target within the 3D scene is detected in a pixel-precise manner. And events will trigger JavaScript, which in turn can modify the 3D scene via the DOM in any way. Like here, this group got an on-mouse over event handler and then calls a function group hovered. There's also an example for this. So we have this model that has an on-click handler and then calls this click function that is given below. And this one is, so the target of the event is the actual model. So we get this element inside our handler function. And then we get the group node, so the parent node, and set some kind of style attribute to modify the transformation. So when I click on this box, it will randomly move up and down. And this happens in a pixel-precise manner. You might hear the clicking. We can also modify this this handler, so it will then move in a much more smaller rate, but however, just to showcase the event handling. Thereby, we can modify the 3D scene in any manner. So there is an option to define meshes and shaders directly. So the mesh can refer external geometry data or define it inline. As you can see here, the first one The first mesh just references the source, which is external, and the second mesh that is completely inline. So it defines a flow3 array, which represents the position, and an index array for the triangles. The same can be done for the shaders, which is above. So you can define the shader properties like the shininess of phone shader, or change the diffuse texture, and this can then be influenced or modified using Xflow, as we see on the next page. We had this wave animation example before. This is some part of it. We declare a generic data block with the data element, and then we attach an operator via the compute to process the data. It is processed from inside to outside. So first, the embedded data container with the compute attribute calculates or generates the geometry of the grid using the Xflow myGrid operator. The result of this is then the input for the next operator, which is the myWave Xflow.myWave operator that takes the position, modifies it to animate this wave and adapts the normal accordingly. And the output is then used by a mesh element by referencing via source the ID wave. And the result finally looks like this. So the mesh element of this one is not part of this code fragment, but what you can see here is we can modify the input to each operator by just modifying the DOM elements. For instance, the strength of this wave animation, and as it now looks weird, we can also increase the resolution of the mesh, which is now dynamically generated once because the result is reused every frame. Yeah, well, you can play around with this. Those operators here are custom operators, so they are not part of XML3D and Xflow as it is delivered, but you can add your custom operators by just including an additional JavaScript file. Thanks. Any questions so far regarding this GE? So it's important to understand how it works because it's the core GE of the Web UI chapter. Otherwise, we will proceed with the other 5 for the first session.
I was just wondering, is there any tool sets for let's create? I was just wondering, is there any tool sets for like creating a scene in Autodesk Max or Maya or something like that?
In the past, we had a couple of exporter plugins for the usual suspects to model 3D scenes, but it's very hard to maintain this. That's why we now go for the approach to use an asset server where you can import your Collada files, for instance, and then retrieve the XML 3D resource for this Collada file. That's tricky as well because Collada can be anything, but well, it's a practical approach. Moreover, there is one exporter for Blender that is currently maintained by the community. So we can expect that this will ease the process to get your assets in there. Any other question? Otherwise, we will follow with the Synchronization GE, which is another GE of the Web UI chapter. This is relevant when creating multi-user real-time web application. What is then commonly needed is the underlying data or C model and the communication protocol to synchronize the data between the participants. So custom buildings of these applications is often not preferable. That's why there is the Synchronization GE. It contains a generic lightweight scene data model and provides the real-time two-way synchronization using server and clients approach. It uses the WebSocket protocol for web clients, and the implementation is based on the RealExtend virtual world technology. There is a reference client and server, so the server and the desktop client, which uses the RealExtend Tundra SDK. The core is written in C++, and it's relatively complex and heavyweight. There's also a web client based on JavaScript, which is called WebTundra. We will get back on this later. There is a demo available. I will not show live here, but it's an end-player Pong, so there can be arbitrary people join this, and it just extends this. The scene data model is based on entities, components, and attributes. So using this Pong game example, the ball and the bats are separate entities, and these contain the functionality, such as the mesh, which is the visual representation, rigid body for physics, and some positioning that is then used to interact with your bat as player. The components contain attributes, for instance, to reference the external meshes by URL. Applications can define its own components as well. To quickly talk about the protocol, so when a new client connects, then the server sends all those entities that are in the world to the client. And after this, there's an automatic synchronization in both ways. So either there is an entity created or removed, or a component of an entity is created or removed, or an attribute of its changed its value. This is synchronized in both ways. So over this this protocol is based on RPC-like entity action to update those entities, components, and attributes. The protocol implementation is available also for, as open source on GitHub. To test this GE, you can just run a server using the command line and then connect via clients, either the desktop client or the web client to this server. The minimal JavaScript client code could look like this. So have a couple of lines of JavaScript code to create your client and retrieve the scene, and then connecting to the server using your login data and so on. So to perform the synchronization, the changes to the scene are sent via the mentioned protocol, like scene entity created, removed, when a component is added, and so on. You can get further information on the FIWARE catalog, and there are also pre-built binaries available on GitHub. The next GE is closely related to this one. We saw the 3D UI GE, which is the core GE first, and the 3D UI WebTundra GE is the implementation of this 3D UI GE to be compatible with the synchronization GE. This all comes from the background of the real extent history. So there is this focus on virtual worlds for some guys from Oulu, and they use their real extent to create open source virtual worlds and games. As I already mentioned, there is this Tundra, which is the virtual world platform, or this framework. But as we now move towards the web, there is the demand of this web-based client. For this, the Finnish consortium that develops this technology has a product called Meshmoon that is based on this Tundra SDK, and this is some hosting service for user-created virtual worlds, and it adds some end-user functionality that the Tundra SDK does not address. There are some examples of games that were created using this. So there's a flight simulator and some Second Life-like party location. But there's also some presentation for showrooms, like the left one is interesting. So that's a real church in Hokipudas, which is part of the city of Oulu, and in this church a virtual mass takes place occasionally with a prize. Well, they did some data visualization using this synchronization mechanism, and also for the building industry, some rendering using the WebTundra 3D UI GE. It's also used for educational purposes like training scenarios and so on. WebTundra itself, I already introduced it, is a JavaScript library that is based on 3GS and the synchronization GE that was presented before. So the asset loading and mapping is all 3GS based, but this also interacts with the 3D UI GE, which is XML 3D. Use cases for this are to build web-based multi-user network 3D apps. So these applications include games, but also like citywide games and any kind of social interaction in virtual worlds. The entity component system I already presented. There is this replication of objects. Here we are now talking about JavaScript objects, which are the representation of those entities. Going via the synchronization GE server. A basic WebTundra application starts with a 3GS WebGL application, and then the logic is added to synchronize those entities inside of the scene, like when changing the attributes like position and so on. To start with this, there's an installation receipt available on FIWARE Lab, where you can set up your own virtual world server and then start experimenting with it. The Pong example is also available as an example in the users and programmers guide of this GE. Yeah, that's the 3-player Pong then, where the WebTundra, as you can see here, this runs in the usual Chrome. Does all this rendering within the browser, and the Tundra server creates those entities like the U-shape areas for each player and receives the bat movement. Yeah, to get more information, there is a dedicated mailing list for this available, as there is already a community around this RealExtend framework.
Last screen. Mailing list. Where is it? RealExtend.
There is the RealExtend dev mailing. I think the URL was in the beginning. It's realextend.org or something like that. There you find help with this. Any other question? Otherwise, we have one GE left for the first session, and we can take a short break. Sorry?
Are there these frameworks mobile friendly? These JavaScripts, these libraries, can we use to make applications and so on mobile devices?
I will show later, but indeed this is Chrome running on the Android that shows GIS application using the XML 3D.
XML 3D, okay.
I will talk about this a little bit later in more detail.
Okay.
This, okay, then we just handle briefly the last GE of the first session, which is the real virtual interaction GE. This is the bridge to all those other IoT GEs you already heard, even that the bridge does not work as it should right now. It is not that major developed GE, but there was a reason to have this. So there is the need for an open specification to interact with those IoT devices, not only receiving data, but also interacting with them, like switching lights on and off and so on. The Real Virtual Interaction GE provides means for connecting real-world devices consisting of sensors and actuators to augment applications. Since the real-world sensors and actors are not complex enough to contain necessary logic to publish themselves outside their immediate domain, there needs to be an external service that is able to access these devices. So there are two main components for the GE. So that's the Real Virtual Interaction Server and an implementation of a reference client. They are talking via web sockets. The Real Virtual Interaction Server will later on talk with the context broker GE that were already presented to you. Yeah, as you're familiar, well, this one, familiar with all those possible use cases around IoT devices like heating systems, bus locations, and room temperatures, which is the usual example. The key features of this GE are to collect and store data from sensors. There are two directional data flows, so the real-time data coming from sensors, but also the data that is going to the actuators. The current architecture looks like this. So there is this server in the middle and some devices that connects to this server, and the end user browser application that retrieve the updates from them. So this GE is used to send the data from devices to this server, and then broadcast it to any client that is connected. There's some additional features like optional compression and some configuration parameters that might be published. There is an API exposed where you can interact with this server from the client side to retrieve the device information or the state of actuators and sensors. There are also some code examples available. I guess they are part of the users and programmers guide to have a more detailed look into that. Yeah, there's just a snippet of JavaScript code below to make the request to change a visualized marker on some display device. Well, we skipped this because we are already late, and yeah, where to get more information. So there is the FIWARE wiki, as you were pointed several times yesterday and today. And there's also the catalog where this GE is available. Thanks for your attention. This would be the end for the first session, and now there is time for questions.
Can we go back to the previous slide, please? Get to first.
This one?
Yes, please.
Yeah, we will share the slides as well.
You found them with SlideShare?
No, I don't use SlideShare, but I will share a link at the end
That would be great, yeah.
of the second
Have
session.
all together.
Yeah.
I don't know who would manage, but couldn't we just have like the program with the links for each of the sessions we have had?
I'm the wrong addressee for this. But
Who should I suggest?
I try to find one. Okay, any other question? Then okay, we will just make a break of 5 minutes, and then we will proceed with the second session on AR and 3D cities.